we're trying to find how much heat was required for this process. So let's draw exactly let's just draw a quick diagram. We have this cylinder, essentially. Let's draw another there. So we have this cylinder, this piston, essentially. We have a force here. This would be the force of the air outside, because of course the force is pushing down if it's outside the container. And then we, of course, have the force of gravity of this piston. We have the mass of this piston, and then a force going up. This would simply be the force of the air inside the piston. We have some givens, so the mass is 0.15 kilograms. We're going to find the area, the surface area of the cylinder. This is 0.08 meters squared. We have delta T. This is going to be 55 minus 25, or just 30 degrees Celsius. We have delta H, 1 centimeter, or 0.01 meters. And we have the outside pressure equaling atmospheric pressure, P naught, or 101,325 pascals. So we should first simply just try to find the pressure inside the piston. So we can say sigma F in the Y is going to equal 0 newtons, because of course this piston is supposed to be perfectly suspended and not moving. So we can say that the force of the air inside the container is going to equal the force of the air outside the container plus the force of gravity of the piston. So we can say P sub in A equals P sub out A, and then plus mg. So P sub in would simply equal P sub out plus mg over A. So we can say 101,325 plus 0.15 times 9.8 divided by A, so 0.08. And we're getting that the pressure inside the container is going to be 101,343.375 pascals. I apologize, 0.375 pascals. Now, we can see piston's weight is negligible. Because again, this number is very close to this number. Simply maybe less than 20 pascals. There's a less than 20 pascal difference between the outer pressure and the inner pressure. So we can say that the piston's weight is negligible. And then we can say that this 1 centimeter height increase is an isobaric process. Where isobaric simply means that the pressure doesn't change. We have the internal energy going to be equal to the degrees of freedom over 2 times nRT. We have a monatomic ideal gas, so this will be equal to 3 nRT over 2. There are 3 translational degrees of freedom associated with the monatomic ideal gas. There aren't any rotational degrees of freedom associated with the monatomic ideal gas, because of course, if you were to rotate it on any one of its axes, it would still look the exact same. So that means that the only degrees of freedom are translational degrees of freedom in the X, Y, and Z directions. Therefore, 3 degrees of freedom for this gas. nRT equals PV due to the ideal gas law. So we can simply say 3 PV over 2. And we can say that delta U is going to be equal to 3 P delta V over 2. Again, this process is isobaric, which means that P does not change, the pressure does not change And we can further define this as being equal to Q minus the work. So at this point, we can say that Q is going to be equal to delta U plus the work. And we can say that this is going to be equal to 3 over 2p delta V. Or the definition for work is going to be p delta V. So we can just say 5 p delta V over 2. And for delta V, we can simply say 5p a delta h over 2, because again, the cross-sectional area of the cylinder doesn't change. However, the height does. So we can simply say that the volume is equal to the cross-sectional area times the change in height. So Q is going to equal, now we can finally plug in and say 5 times 101,343.375, that is the pressure outside, times 0.08, and then times the height difference of 0.01 meters, and we can divide this all by 2, and we're getting 202 joules. So 202 joules of heat are needed in order to complete this process, in order to move the piston up 1 centimeter. That is the end of the solution. Thank you for watching.